About exponentials again. Just kind of rehash as a quick introduction yesterday. But an exponential function, by definition, is a function in which you have a base raised to some variable exponent. Your base it has to be greater than 0, but it cannot be 1. Okay? Because if it's 1, it's kind of boring. It's actually linear if it's 1. When we look at an exponential function, depending on the base can be, like I said, anything between 0 and 1, so all of those fractions. It could be 2, 3, 4, anything between those things. But regardless of what your base is, every exponential is going to kind of have the same behavior. Okay, so if I look at 2 to the x, and then compare that to 3 to the x, compare that to 4 to the x, which is what we'll do here in a little bit, you should still see similar behaviors. Okay, so I've got 2 to the x up there. And the one thing we talked about yesterday is at this point right here, that blue point A will always be a key point for every exponential, right? Because think about taking any number as a base. Doesn't matter what your number is, and you raise it to the 0 power. You were taught in Algebra 1 when you first introduced exponents and laws of exponents that you said whenever I raise something to the 0 power, you get back what? 1. Okay? So anything raised to the 0 is 1. So 2 to the 0, 3 to the 0, 4 to the 0, e to the 0. They're all going to pass through 0, 1. So that is a point that we want to commit to memory. All right? The other points, B. Okay? So let's look at point B here. That point, 1, 2. Okay? Well, think about this. No matter what my base is, if I raise it to the first power, what do I always get back? Same thing I started with, right? 2 to the first gives me 2. 3 to the first gives me 3. 4 to the first gives me 4, right? So 1, my base will be a critical point on every single exponential function. Okay? And then over here, the same concept happens with this red one. It's a little bit more work with the red one to figure out why this works, but whenever I raise 2 to the -1, or 3 to the -1, or 4 to the -1, okay, whatever my base is, if I were to just do a little bit of work here, show you the algebra, if I say I've got 2 to the -1, we never write it that way, right? We don't like negative exponents, and it's really 2 to the -1 over 1, right? Well, to rewrite that so I don't have negative exponents, I'm going to take the base that has the negative exponent, and I'm going to put it in the denominator down here. And that gives me 2 to the 1, right? And now what would be left up here? 1. Okay? So when x is -1, the y value you get back is 1/2, right? Okay? And that is simply the what of your base. 1/2 is what of 2? That's the reciprocal. Okay? And we start to see these as I move this a term back and forth. See if I can clear some stuff out here real quick. If we move this a value, well, I guess I didn't do it that way. Let's do it this way. I don't think I've used R. Won't let me use R. All right. Okay, so as I move the base, now obviously 1 is not exponential, right? So we start maybe at 2. We get 1, 2, 0, 1, -1, 0.5, or 1/2. Move it to 3. You get 1, 3. Still get 0, 1, right? And now -1, 1/3, right? Move it to 4. Get 1 comma 4, 0 comma 1, and now negative 1 comma 1/4. So we talked yesterday towards the end of class that every single exponential, okay, if it's written in the form f of x equals a to the x, where a can be anything bigger than 0, but not 1, okay, then you will always have the ordered pair 1 comma a. You will always have 0 comma 1, and then you will always have negative 1 comma 1 over a. Those are 3 points that every single exponential function is going to have. Okay. Now I say that, but every single exponential function that has not moved left, right, up, or down, or been vertically stretched, shrunk, that kind of stuff, right? So before we do any transformations to these things, every parent function, a base raised to the x value, or the x variable, is going to have those 3 points. And if you have those 3 points and understand those 3 points, then when we do transformations, we move things left or right, those are the 3 points you want to move left or right. Those are the 3 points you want to move up and down. Those are 3 points that you want to stretch or compress. Okay? And that will get you then the infinite family members that we see that we're going to have graphed over here on the left-hand side here in a moment. Okay? So let's say that I have, let's go back to allowing that to be 2 to the x. Okay, and I'm going to show G here, and I believe I need some other numbers that no, A is the only one. All right, so let me hide that. Change this. Let's just go by integers. All right, so when I look at, obviously, we have this green curve. Let me put the name of the green curve on here. All right, so we look at the green curve, and right now it's 2 to the x, right? It's the same thing as the maroon curve. But when I start moving that slider there, it starts to subtract from x's, right? So we have 2 raised to the x minus 1. What happened to this point right here? It went to right there, didn't it? Okay. It's a movement which direction? To the right, correct? What about this point here of 0, 1? Where did it go? Went to the right 1 unit, right? Went to 1, 1. This point of 1, 2 went to 2, 2, right? Okay. So my hopes are is that you can see that this entire curve, see if I can do it this way. Let's go. Well, it won't let me move it, but that point got moved 1 unit to the right. That point got moved 1 unit to the right. That point got moved 1 unit to the right. Okay. And then every other point, maybe one right there, gets moved 1 to the right, correct? Does that make sense to everybody? And is that consistent with what we've talked about with other functions? When you subtract from the x value before running that parent function through its steps, okay? So what I'm saying there is the overall function is a exponential here, right? So before raising anything to an exponent, I actually adjust my x first, okay? So I do x minus 1, and then I raise that quantity as my power. I raise 2 to that power. That is always going to move your function horizontally, okay? If it becomes x minus 2, then we see that those vectors are screwy the way I've got them set up. But if I go x minus 2, it moves it to the right, so that point went over here, 2 units to the right. That point goes right there, 2 units to the right. This point, all the way over, 2 units to the right. Does that make sense? Okay. So if I were to highlight them, I should get, and this is where I think it's important to understand those blue points, okay? If the blue points are key points on 2 to the x, okay, then x minus 2 should take the x values and add 2 to all of them. So I should have 3 comma 2 show up. I should have 2 comma 1 show up, and I should have 1 comma 0.5 show up on my new curve, right? So my hopes are that you guys realize if you understand the parent function points, those 3 points, you should be able to adjust those based off your transformations, moving left, right, up, down, stretching, shrinking, and develop any one of the kind of family curves that can be created. Is that doable? What happens if I subtract? Or sorry, when I subtract, it moves it to the right. So what happens if I add? Yeah, okay. So moving, x plus 4 is going to take that red curve and move it to the left 4. Something we haven't talked about, which I think warrants some discussion, it should always warrant discussion when we talk about a new function, is the domain and range. Okay? If I look at 2 to the x, okay, look at that function right there. What's this domain? Negative, fade, positive. Nothing gets kicked out, right? You can plug in any x value you want to, and you get a y value back, right? Okay. Now, the y values you get back are going to grow extremely fast, okay? So, for instance, if I see, let's see if I can do this real quick. If I go, let's just say, let's create an ordered pair. We'll call it m comma f of m. It's going to ask me to create a slider for m. We see some order. So when I say m comma f of m, it's going to take the value that is on this slider here, okay, and it's going to let that be my x value. So right now it's at 1, okay, and then it's going to take that 1 and plug it into my function 2 to the x. So it gives me 2 to the 1, which is 2, right? Now I'm going to take that slider. I'm going to make it go from 1 to, let's just go, I don't know how far to let me go. Let's go 10,000. Go by ones. All right. So when I go m to be 2, it's now 2 squared, right, as my y value. So 2 to the 4th. So we're kind of focusing on that point right there. It's really, let's see if I show the label of that. The ordered pair at least. We're going to point D here, 2 to the 4, okay, or 2 comma 4. Then when I make it go to 3, it's going to go 3 comma 8. I make it go to 4. It's going to go up to 4 comma 16. And the idea of exponential, you hear people say grew exponentially, right? That means it grew really fast. Are my y values going up really fast? I'm at a pretty small x value, right? But my y value is 16. It's pretty large. And when I go to 5, 2 to the 5th is 32 now, right? 2 to the 6th is going to be 64, something we don't want to graph ever by hand, right? But let's think about, let's just look at this ordered pair down here because I'm not going to want to zoom in and out all the time here. If I start moving that, look how fast those y values get. 18 is a relatively small number, right? But look at the y value that goes with it, okay? So I'm taking 2 and multiplying it by itself 18 times, right? Well, if I keep doing that, do you see at that x value, or sorry, the x value is increasing without bound, right? Okay, I have no limits on my x value. Does it look like there's going to be a limit on my y values? My y values get pretty big, right? Now, 100 is a relatively small number. But look at what I get when I raise 2 to the 100th power. Okay? Now, okay, now, the undefined, what it's doing is basically telling me that it doesn't have the ability to calculate it. Okay, I think, like if I do this, let's say, instead of using the slider, let's say that I have let's go 100,000 as my x value, and then I compute f of 100,000. See if you gave me the point. Nope. I forget what I was doing. Last period I did it, and it gave me 100,000 comma infinity. Actually, GeoGebra has the ability. I just think it's the way I've got it kind of programmed today, at least most portion. That's not the right point for some reason. But what I want you to see, I want you to understand, is that your y value increases without any boundary. Okay? Your x values increase without any boundary. So my domain is all real numbers. Okay? My range, we need to understand that. I said your y values increase without any boundary. Okay? But what is the smallest y value that I can have for these things? If I look at 2 to the x, if I look at that red curve up there, what is the smallest y value? Think about this. Remember, dealing with range, don't we want to take a horizontal line and move that horizontal line vertically until it starts to intersect our curve? And then where it starts to intersect our curve, we start recording those values, and those values, those y values, become our range, right? So the first, now it's not the first value that I intersect, but what should be the first value in the y's that I start talking about? 0, okay? Because if we zoom in here, we're getting infinitely closer and closer to 0. Good, okay? But we'll never get to 0, right? So we need to talk about that somehow. We can't say that our first y value is like 0.000000000000001, because even though there's a lot of zeros there, that is actually really, really, really big compared to the first y value that we should really be getting to. Okay? So the first one we want to talk about is 0. We put a parenthesis around it, right? And now what would be the last y value? What was kind of the exercise that we showed here with that slider? This y value here is going to increase to what? Infinity. Okay? So your range goes from 0 to infinity. All right? Domain is all real numbers. Range 0 to infinity. What if we do this? What if I say, back to standard view, what if I go from 3 to the x? Is that range and domain the same as 2 to the x, as 4 to the x, as 10 to the x? Are those domains and ranges all the same? Yeah, okay. It just means that my curve gets, when I change the base, it just means it increases a lot faster. Okay. You're seeing over here, I think this is maybe something to talk about as well. To the right of 0, my x values are larger than 0. Then you see that this curve is growing faster than any of these, right? Okay. But when I look between, I guess to the left of 0 over here, you see that now that curve is not growing as fast as the other ones, right? The orange curve here is the y values are slower to increase over here because of the reasoning of what we do with negative exponents. Is 10 raised to the negative 1. That's 1 over 10, right? That value, 1/10, is that less than 4 raised to the negative 1? I guess 4 raised to the negative 1 is 1/4, right? So 1/10, okay, right there, where my cursor is obviously a smaller value than that blue curve of 1/4, okay? So on the right-hand side, they increase faster, okay, with a larger base. But on the left-hand side of the y-axis, they kind of increase slower the larger the base, okay? But they all pass through what? Common point, 0, 1, right? They all pass through that, okay? But they all have the same range. They all have the same domain. What if I do this, though? What if I take, let's just look at 3 to the x, but then I write it as 3 to the x plus 4. Did the range change? What's the first y value that you would see on that top curve here? It's gray. Let's change color. What would be the first y value you see on that red curve? Careful. It'd be 4, right? Okay. Now it would be 4.00000, however many zeros you'll put there. So we put a 4 in a parenthesis, okay? But the range is now different, right? Okay, because of that vertical shift. When you shift a function that has asymptotes, the asymptotes move as well. Okay, so you had initially an asymptote. The purple one has an asymptote of y equals 0. When I shift that 4 units up, my red one has an asymptote now of y equals 4. Okay, does the domain change? Nope, all real numbers. Okay, you're not going to be able to do really anything to this thing to change the domain. You will do things to change the range, though. Okay, let's go. What happens when you take a function and you multiply it by a negative out in front? Reflects it over what? X-axis. Okay, so I get that curve, right? Does the domain change? No. Okay, does the range change? Yeah, the range is now what? Negative infinity up to 0. Right? Remember, we want to write that as a number line left to right. Largest negative number first, and then all numbers greater than that second. So negative infinity up to 0. A lot of people want to go 0 to negative infinity when they write that range. Make sure you always look, range is always bottom up. Okay. What if I would have done this? What if I would have taken 3 to the x, and instead of multiplying the 3 by a negative, I come to the x and I multiply it by a negative. What's that going to do? Yeah, flips over the y-axis. Okay. Now that looks something similar to what we've already talked about. I think we maybe introduced it yesterday. That looks the exact same as we can have bases that are fractions, right? Between 0 and 1. Okay. So we're going to go 1/3 raised to the x. Do those two curves overlap? Why? Why? Okay, so if we, let's do this. Let's do a little bit of algebra here. Let's go. Oh, they want that. Do we know that if let's just start with the f of x equals 3 to the negative x. Is that the same thing as saying 3 over 1 to the negative x? Okay. Is that the same thing when we have, going back to your laws of exponents from Algebra 1, maybe a little bit, you talked about them in Algebra 2 as well. If I have like a raised to the m over b raised to the n, and I raise both of those to maybe like the r power, can I rewrite that as a to the mr over b to the nr? Remember doing that? Okay. So is this a 1 there and a 1 there? These exponents of 3 and 1? They're understood exponents, right? We don't usually write them there. But can I do that power to a power then? Can I take 3 raised to the first? So I take that 1 and multiply by a negative x and get 3 to the negative x. Does that make sense to everybody? Can I do the same thing down here to the 1 then and rewrite that as 1 to the negative x? And do we like negative exponents? No. So if it's a negative exponent, the base and that exponent need to go where? To the denominator. So that 3 to the negative x to go to the bottom here and rewrite it as 3 to the x, right? And now that's 1 to the negative x to go to the numerator, and I write it as 1 to the x, correct? Okay. Well, I'm going to use the word distribute here. When we distributed that there, okay, can we undo that at this stage? Can we pull that x back out and get 1 to the 3rd raised to the x? Does that make sense to everybody? And the reason we can do it, the question I always have is, well, is that legal? Can I do that? Well, if I make those 1s right there, and I use my law of exponents, I take that x times that 1, I get 1 to the x, which is that thing right there, and I do the same thing with the 3, and I get 3x, which is that thing right there, right? So I do know that 1 to the x over 3 to the x is the same thing as 1/3 raised to the x. Now, is 1/3, have we just shown then that 3 to the negative x is identical to 1/3 raised to the x? Okay, so I think, personally, I like to look at the 1/3 raised to the x a little bit better algebraically than 3 to the negative x. So whenever I get 3 to the negative x in a textbook or working on something in a course, I always use that property and say, oh, I know that's 1/3 of the x. Okay, I'd rather work with positive exponents. Does that make sense? Just something to think about as we go through these things. Now, if we're dealing with these types of functions moving, when basically you have a base that is a fraction between 0 and 1, it is no longer, exponential means when we say exponential, we're thinking grows large very fast, right? Well, this one is shrinking very fast, right? So a lot of times we talk about exponential in regards to growth, but we can also talk about exponential in regards to decay, right? Does that make sense? Yeah, you guys remember talking about like half-life and stuff like that in chemistry? Okay, those are exponential, okay? And we'll actually talk about a lot of applications of exponentials and logarithms, and half-life is one of them, okay? These functions have a great role in explaining things like half-life. You guys ever heard of Newton's law of cooling? Let's say that I have a cup of coffee, take it out of the coffee pot, set it in a classroom or just any room, and I know the temperature of that room, and I know the temperature of the coffee. I should be able to determine without even using a thermometer, after how many 10 minutes maybe, how cool that coffee is. Or I can determine the length it's going to take until that coffee reaches room temperature. Okay. Anybody like forensic science? See, like, you guys watch like CSI and stuff like that? Law and Order. Okay. So somebody comes across a dead body, okay, and coroner goes and takes the temperature of the liver, right? And they're able to, from that temperature, determine the time that body has been there. Okay. Now there's actually there's some parameters to that if the body's been there for 15 days, they can't really do that. But if they can tell that it's been a recent crime, they can take that temperature, take the temperature of the ambient room, okay, the ambient temperature, and use Newton's law of cooling, which deals with exponentials and logarithms, and determine the time frame in which that body's been there. Okay. You guys ever heard of the Richter scale?
Yes.
Okay. Now we don't use the Richter scale anymore. I forget what it's called. When we get to it, we'll talk about it. But the Richter scale tells the magnitude of earthquakes, right? That is based off of logarithms. I think we talked yesterday how like the seeds of a sunflower kind of position themselves logarithmically. But when I say logarithm at the same time, I'm talking exponential, right? Because they're inverses of one another. So there's a lot of real life phenomenons that we can use exponentials for. We'll actually see one here in a couple minutes. But this is kind of a decay idea. Okay, so whenever you see growth or decay, those phrases, we're dealing with exponents, okay, or exponential functions. But again, let's think about this. I should still have the point 0, 1, right? 0, 1 still show up there? I should have the point 1 comma my base, right? 1 comma a. What is my base in this case? Looking at the red one. 1/3, right? Do I have 1 comma 3? Okay. And I should also have then 1 comma 1 over my base, right? And I'll even write it that way. All right, 1 divided by my base of 1/3. Well, all right. Oh, sorry. I want -1. -1 over 1 over my base. So you got that point there, right? Okay. So I still have the point 0, 1. I still have the point 1 comma a, and I still have the point -1 comma 1 over a. Does that make sense to everybody? Whether the graph is increasing or decreasing. Does the domain change there? Still all real numbers, right? Is the range still 0 to infinity? Yeah. Okay. So as you work through homework assignments, they're going to ask you a lot of stuff about these functions. But the transformation, what I'm trying to hopefully press upon you is that the transformations, if you knew the transformations for x squared, if you knew the transformations for x cubed, you knew the transformations for x to the first, then you know transformations for exponentials. Okay? But what is important, and I don't know if I talked about this with you guys yesterday, I did talk about it with the last class. If I'm dealing with that exponential, eventually we want to graph logarithms. Okay? And then that's going to be in 2 sections from now. But logarithms undo exponentials. So mathematically, when I say the word undo or undoes, what math term should come to mind? Inverse. Okay. So if an exponential and logarithm undo one another, they should be inverses, correct? Okay. So they should be reflections of one another across that line right there, right? Okay. So in the event of graphing a logarithm, they give me this logarithm. I'm actually going to use our rule about logarithms and exponents, and I'm going to actually change it to an exponential function. And I'm going to graph the exponential function. And then when I get that exponential function, and I know that it has, in this case, 0, 1 on it, and it has 1 comma 3 on it, and it has -1 comma 1/3 on it, and I want to graph its inverse, its logarithm. What happens to those ordered pairs when I want to graph the inverse of anything? Remember the key idea that happens if I look at point B, which is at 1, 3. What is the point that you know should happen to exist on its inverse? 3, 1. Okay, so 3 comma 1 should show up. Now I have 0, 1, so 1, 0 should show up, and then I have 1/3 -1 should show up. And if I ask this, then what this will do is actually reflect this across the line. What did I do? Oh, I typed in 3, 2. Stupid. 3, 1. Okay. And we then see that curve, and that curve is then a logarithm. Does that make sense? And we'll talk in a couple days about what logarithm that is, and you guys already know how to create logarithms from the exponential and vice versa, but we'll do that later on. Is that all right? Okay, so hopefully that's enough discussion about transformations with these things. Let's get to an application. All right. The more and more we do mathematics, the more and more the hope is that a lot of things that we use can be, or that we do in class, can be applied somewhere. Okay. There's a lot of mathematics. There's a lot of mathematics out there that is just developed because of human curiosity. And I gave the example last class that prime numbers. Okay, before kind of the advent of computers and all that kind of stuff, prime numbers, there's a huge branch of mathematics, and there still is a huge branch of mathematics because technology, it's getting even bigger about just dealing with prime numbers and trying to find out what is the next prime number. Somebody, a long time ago had the interest to say, okay, we know that 3, 5, 7, 11, 13, those numbers are only divisible by 1 in themselves, right? They'd say, okay, well, does that list ever end? Is there a last prime number? Okay, because the larger our numbers get, the more composite they get, and early on we have a lot of prime numbers in our number line, right? But as I move on along the x-axis and in a positive direction, the further I get out there, the gap between consecutive prime numbers becomes very, very, very large. So the idea is that, well, that gap is getting larger and larger, so prime numbers are starting to dwindle. So people are thinking, well, eventually they're going to dwindle down to 0. We'll have a last prime number. So the branch of mathematics is kind of going through that and trying to figure that out. The idea is that we will have infinite prime numbers eventually, but they want to find and there's contests and stuff like that out there that what is the next prime number? You build a supercomputer that will determine the next prime number. And early on, that was just human interest. We were just concerned, we were curiosity or whatever to figure that out. But then the advent of computers and security and passwords and encryption, you ever heard of encryption? Okay? Encryption works because of prime numbers and very, 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 very large prime numbers. So this human curiosity that people were using or developing this stuff with actually led to something very useful. Okay? And without those large prime numbers, we don't have secure bank accounts. We don't have secure passwords and stuff like that. Okay? So the more math that you guys learn right now, up until this point, I think maybe a lot of the math that we've done is the building blocks for being able to apply something else later on. Okay, and this is one of those situations where we actually take something we've learned and use it. Okay, I'm not going to right now in class give you the formula or the proof of this formula. It's actually pretty easy proof. It's just factoring basically, but I will put together a video, I'll probably do a third period, of that proof of this formula. Okay, it's the compound interest formula. And what the compound interest formula is dealing with, interest is based off of the idea is, I put money into an account, and it sits there with an interest rate, and it sits there for a certain period of time. How much money after 2 years, 3 years, 4 years, whatever, will I be able to have when I take that out? Okay? So the bank is basically paying me to leave my money in their coffers. Okay? And then, they take my money then and they invest it somewhere else, and they start making money off of that. But my money is always my money, and I can go get it anytime I want to. Does that make sense? Okay? When we deal with that, banks offer what they call a compound concept, okay? And the idea is if I have $100 and I invest that into, or just put it in a savings account or whatever, when that $100, and I leave that in there for 10 years, my hopes are that that $100 is not the only thing that's earning me money. Does that make sense? Because after a year, depending on whatever my interest rate is, maybe that $100 has grown to $101. That's usually what bank accounts do. They grow, or savings accounts grow very, 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 very slow. $1 is actually a pretty big, a 1% interest rate is actually a big amount for a savings account. But nonetheless, if I leave it in there for a year, that $100 has now grown to $101. My hopes is that in year 2, instead of the $100 creating interest for me and creating extra money for me, that the $101 creates interest for me. Does that make sense? That extra $1 now adds to my interest, and it gains money. It does work for me. And that idea to get that to happen is called compounding, which basically means that they roll over all the interest you've made, they add that back to the principal, and then start the whole process back over with a new principal. Okay, which includes then your original principal plus what growth you made. Okay, so you get this formula here: P times 1 plus R divided by N. Now R divided by N, R is your interest rate, and N is the number of times that they're going to compound. Okay, and a lot of times they'll compound it, maybe twice a year, maybe 4 times a year, maybe once a month. Okay, maybe once a day. Okay, so N is going to change, and then raise to the N times T. And like I said, I'll give you a quick proof, just because of time. I don't think it makes sense right now to do that, so I'll do that in a video. But what these values stand, what these variables stand for, P is your principal, so principal is the initial amount that you're going to be placing into this account. Okay. Sometimes people call P, sometimes folks will see it as capital A sub 0. Okay, and anything sub 0 is initial, right? Okay, so initial amount or principal. R is your interest rate. Okay, remember, and that's got to be, they're going to give it to you as a percentage. You can never put a percent into math, right? It's got to be a decimal. Okay, so you got to convert that percent to a decimal. Number of times interest is compounded per year. That's going to be provided using words like annual, semi-annual, weekly, monthly, daily, that kind of stuff. We'll talk about what those mean here in a little bit. And then number of years that process is going to, or that money is going to sit in that account. So 1 year, 2 years, 3 years, whatever. Okay? So when we do this, I'll give you kind of a quick example here, and then obviously work a lot more on this next week. But it says a sum of $1,000 is invested into an interest rate of 12% per year. It says find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay. Now that's like 6 problems in one. Okay. But we're going to use our calculator here. So the hopes are that once you do one of these, you're able to do all of them pretty easily. Okay. But they give you all the information we need. So I'm going to write down my formula here. It says A of t. Okay, A of t, that stands for the amount after a particular time. Okay, so A of t is equal to my principal. What was my principal? $1,000. And now 1 plus my interest rate was 12, right? 12%, so I write it as 0.12. And now let's do this one here, semi-annually. Okay, annually is boring. Annually is just a 1 right here, right? Okay. Semi-annually, what's that mean? 2. Okay, it means we're going to do it twice a year. Okay. So you said 6. So you're thinking months, right? Yeah. Okay. You got the right concept. And then raised to the n times t. N being the number of years that it's going to be, n being the number of compounds, so 2, and then t being the number of years that it's going to be in that account. Now, most of you are going to say, well, why'd you write it as 2 times 3? No, just write it as 6, right? Well, I'm going to use my calculator here in a moment. And I think using it as 2 times 3, writing it as 2 times 3, is going to be beneficial for my calculator. Okay? So this should tell me then, when I type this in, let's see if we can get this big screen for you guys. I'm going to go 1,000, put a parenthesis, and now I go 1 plus. Now, you don't need to do this. I'm just weird about my parentheses and my order of operations, so I'm going to put my r divided by n inside its own parentheses. Okay. And then I'm going to raise that to the, now most people would probably type 6. But I'm going to type 2 times 3. I'm going to show you why here in a moment. Because it's still, the calculator still knows it's 6, right? And if I put parentheses around it, the calculator knows to do that first. So when I hit enter, it's going to tell me this $1,418.52. So I made $400 in 3 years. Okay? If I just let my money sit there, right? Okay? Probably a pretty good deal. But the next thing is to do this quarterly. Okay? Well, quarterly means how many times a year? 4. Okay? I don't want to have to type all that stuff in again. Okay? So I'm going to hit second, enter. And when I do that, I'm able to go back through and change the things that need to be changed. And the only thing that needs to be changed is n, right? Everything else is consistent. So n previously was 2, now it's 4. So I go to that and change it to 4. Go to that 2, change it to 4. And now I've got it for quarterly. Made a little bit more money, right? Well, what if I want to go monthly? Hit second, enter. Okay. Come up here. Now the 4 needs to go to a 12, right? So if I highlight and just start clicking 12, it's actually going to go over my parentheses. So actually, I need to use the insert key. So I go to the 4, hit second, and then delete, which is the insert key. And it should change my cursor to that. And what that's going to do is it's going to put the next button I push will put a number in front of 4. Okay? So I want it to become 12. So I'll put a 1, and now I can adjust the 4. I just push left and right to get back to that block cursor, and then push 2. Come down here to this 4, do the same thing. So second insert, 1, move to the right, come back, change that to a 2, and then 1430. So I make a little bit more money. Does that make sense? Now the goal is with the process, the reason I do it that way is because pretty much on all your questions, you're going to say, do it monthly, do it yearly, or quarterly, do it daily, do it twice a day. Do it 4 times a day. Does that make sense? They're going to ask you 5, 6, 7 different questions, and I don't want you to have to type all that stuff in 5, 6, 7 at a time. Dad?
Okay.
Are you serious? Let's see.
Every other grade is like